Prove each statement in 8 through 23 by mathematical induction. For any integer n greater than or equal to 0, x to the n minus y to the n is divisible by x minus y, where x and y are any integers with x does not equal y. So the first thing I'm going to do is I'm going to identify what my propositional statement P of n is. And now we can jump to the base case. Since n is greater than or equal to 0, that means our base case is going to correspond to when n equals 0. So I'm going to write P of n, but I'm going to replace all of my n's with 0. So this would be x to the 0 minus y to the 0 is divisible by x minus y. Now what I should have done is I should have assumed that x and y are integers with x is not equal to y. So we're going to assume this before the base case, just to give proper context to this proof. So we assume that x and y are integers with x not equal to y. Then x to the 0 minus y to the 0 is divisible by x minus y. I'm going to put a question mark here so that we don't assume the conclusion. This is a thing that we need to show in the base case in order to prove that the base case is true. So I put a question mark to avoid asserting the conclusion in line 1. We don't want to do that. We want to reach this conclusion. And by putting a question mark, I avoid making a claim. Now, x to the 0 minus y to the 0 is just 1 minus 1, which is 0. But that's technically assuming that neither x nor y is 0. And so we would technically need to create a special case for those specific instances when x or y is 0, because raising 0 to the 0th power is problematic. But it looks like we're not really concerned with that specific case. So I'm just going to assume that neither x nor y is 0 in this context. Now we need to show that 0 is divisible by x minus y. Why might that be? Well, we can write 0 as 0 times x minus y to show that 0 is a multiple of x minus y, and this means that x minus y divides 0. So that's the base case. Now let's do the inductive step. So the beginning of the inductive step is always the same. Let k be an arbitrary fixed integer with k greater than or equal to 0, and assume that p of k is true. The first thing we should do is we should write out what p of k is. P of k is what we get when we take p of n and we replace n with k. So this is going to be x to the k minus y to the k is divisible by x minus y. But we can actually write out what that means. That means that x to the k minus y to the k is equal to some constant z times x minus y for some integer z. Next, let's write what we want to show. We want to show that p of k plus 1 is true, which would be that x to the k plus 1 minus y to the k plus 1 is divisible by x minus y. So we want to take this expression x to the k plus 1 minus y to the k plus 1, and we want to somehow factor out an x minus y. We get to use this fact to do this, but I will warn you, this is going to be pretty tough to do. Now, if you notice in your textbook, there's a hint which says that x to the k plus 1 minus y to the k plus 1 equals this thing. Now, I'll admit, if you don't use this hint, it's going to be really, really difficult to get to this step here. I tried a couple different strategies and I really had to use the hint. The hint basically tells you to subtract this special term and add that term. And by doing so, you can have this special factorization. With this special factorization, we can use the fact that x to the k minus y to the k equals z times x minus y. So we can rewrite this as x times z times x minus y, and then plus y to the k times x minus y. And that's by the inductive hypothesis. We're using the inductive hypothesis to rewrite this x to the k minus y to the k as z times x minus y. And now we can factor an x minus y from both of these terms and write this as x minus y times x times z plus y to the k. And what's important here is that this is an integer, which we can call s. And so let's summarize what we have shown so far. We have shown that x to the k plus 1 minus y to the k plus 1 equals x minus y times some integer s. And this means that x to the k plus 1 minus y to the k plus 1 is divisible by x minus y. And that is p of k plus 1. So this means that p of k plus 1 is true. And this is the part where we end the mathematical induction proof by saying, by mathematical induction, p of n is true for all integers n greater than or equal to 0. Thanks, everyone, and I'll see you in the next video.